Hello everyone, my name's Jordan Beim and I'm a postdoc at the University of Minnesota, and in this video I'm going to give you an overview of the tools we are providing for you to use in the CI Hackathon, as well as some instructions on how to install and use them. The toolbox we provide contain a set of functions that simulate the sound processing of an advanced bionics cochlear implant. In brief, the audio signal is first pre-processed, then divided into channels for per-channel processing, where envelope extraction, noise reduction, peak frequency estimation, and current steering algorithms process each channel separately. Finally, the channel data is mapped to the electrodes of the cochlear implant, and electric pulse generation is simulated using the same parameters that exist in the real devices. Each one of these processing steps is its own functional module in the toolboxes we provide. For a deep dive into the CI simulation code, including the technical details of how many of the processing modules here work, please check out the video presentation by Philip Herrmann from Advanced Bionics. During the contest, you may choose to focus on enhancements or signal processing of the audio before it is processed by the CI simulation toolbox, or make modifications to the default strategy that we provide by adding, removing, or modifying the processing blocks shown on the screen, or by a combination of both. In any case, the result of your work will be to produce an electrode matrix containing the electrode pulse patterns over time, or electrodogram, for each of the 16 channels available on a modern Advanced Bionics cochlear implant. Your electrodograms produced by a variety of acoustic inputs will then be used as your submission to the hackathon and will be judged using the final tool in our processing chain, the vocoder. The vocoder converts the output of the implant simulator, the electrodogram, which again is a matrix of current amplitudes plotted by the individual channels, shown here on the right, into an acoustic representation of what a real cochlear implant patient might perceive. You can and should use this tool as part of your workflow to evaluate the effects of your novel signal processing on the information transmitted by the implant to the patient. The vocoder can save audio files for your own comparison, but all valid submissions to the hackathon must be the electrodogram matrices, not the audio. Our vocoder is included with the implant processing chain, but it is intended to be a standalone module. While the full source is available, you should not spend any time trying to make modifications to the vocoder as part of the contest, since we will be using the default version provided to you as the source for judging once the submission phase of the contest is over. Now that I've given an overview of the toolboxes, the rest of the presentation will focus on how to acquire and install them. We provide the full simulation toolbox, including the vocoder, in separate repositories for both the MATLAB and Python programming languages. Each language has slightly different requirements. MATLAB requires at least release 2015A and the signal processing toolbox in order to run. The Python toolbox requires Python 3 and some other dependencies to work. The full list of those dependencies for Python can be found on the GitHub page in the README section. You can find links to the GitHub repositories for each toolbox on our website. The toolboxes both include a README with instructions for installation and the list of dependencies, and all the code necessary to run the full implant simulation processing chain. They each include the same set of documentation, which was originally designed for MATLAB, but the MATLAB and Python code has the same functionality and operates on nearly identical inputs. Lastly, they both include the vocoder module for listening to the results of your signal processing without having to go through the submission process on our website. To install the packages, we recommend first configuring your environment with the required dependencies. For Python, we recommend the latest version of the Anaconda Python distribution. There are additional dependencies for Python outside the standard libraries that are bundled with Anaconda Python. The Python Git repository has all of the details about the necessary libraries with some insight to their purpose within the toolchain. The dependencies can be installed through pip or conda. For MATLAB, release 2020A is recommended, but versions as old as 2015A should still work. Be sure that the MathWorks signal processing toolbox is installed before trying the code. Installing the package is as simple as cloning the package in your preferred language from the repository. We should note here that we're not allowing branch creation or pull requests for contest entries, so create your own repository in GitHub if you wish to do your source control there. Each package has its own post-download routines to completely enable its functionality. In both cases, all you need to do is run a script to complete the installation procedure. In MATLAB, the script is called GMT start, and in Python, the script is called installer. Once you have the files installed, you can test the packages by running the demos. In MATLAB, find the file demo4procedural and run it, and in Python, run demos.py. Each demo provides the same example of the signal processing steps, starting from the acoustic input to the electrodogram output. This concludes my overview and installation guide presentation. PDF copies of the slides are available on our website as a static reference if you need them. And if you have any questions about our toolboxes or run into any technical issues while trying to install or use them, please reach out to us on the Hackathon Slack workspace. You'll be able to find a link to that on our website. Thanks for watching, and good luck.